In 1707, Admiral Sir Cloudesley Shovel led his British fleet home after his victory against the French Mediterranean forces near Gibraltar. A thick fog hounded them for 12 days at sea, and Shovel was afraid they might run aground on the treacherous coastal rocks. Therefore, he gathered all the navigators together to get a consensus on their location. They concluded that they were safely west of the Brittany Peninsula. Thus, they began steering northward. Unfortunately, they miscalculated their longitude and they smashed into the rocks of the Isles of Scilly, sinking 4 of their 5 warships and losing about 2,000 men. This disaster, like so many before it, finally prompted Parliament to action. This was a moment in history called the Longitude Act of 1714. To navigate the vast oceans, one must first understand their position on Earth. Imagine the Earth as a grid marked by 2 sets of imaginary lines, latitude and longitude. Latitude, running horizontally, measures your position north or south of the equator. Sailors could easily determine their latitude by measuring the angle of the sun or stars above the horizon. But longitude, the lines running from pole to pole, was a different story. Measuring one's east or west position from a fixed point, usually Greenwich in England, was not so straightforward. Determining longitude was a game of guesswork, often with disastrous consequences. To help solve this conundrum, the Longitude Act of 1714 was passed by Parliament. It would award a prize of £20,000, which is about $55 million in today's money, to anyone who could find a practical method for precisely determining a ship's longitude at sea. A contest of this sort was not new. In 1598, King Philip III of Spain offered a similar reward of 6,000 ducats, roughly 1.2 million today, for anyone who could solve longitude. In the quest to conquer the longitude problem, explorers and scientists primarily pursued 2 avenues. The first was celestial navigation, an age-old technique that looked to the stars, the moon, and other celestial bodies for guidance. This method seemed promising. By meticulously measuring the angles between these celestial objects, navigators could theoretically determine their exact position on the globe. However, this approach was fraught with difficulties. Precision was paramount, not just in observation, but also in the complex calculations that followed. Navigators had to rely on extensive astronomical tables to interpret their measurements. The process was vulnerable to the whims of nature. Cloudy skies and turbulent seas could render observations useless. Even with the perfect equipment and clear skies, the navigator faced another hurdle, mastering the intricate art of celestial calculations. This required extensive training and experience, making the method cumbersome and impractical at sea. The second strategy hinged on an elegant principle. Time is intrinsically linked to the Earth's rotation. Our planet completes a full rotation of 360 degrees in 24 hours, which translates to a movement of about 15 degrees every hour. This consistent motion offers a clue to longitude. Imagine if you could determine the local time where you are at sea, and simultaneously know the time at a fixed reference point, such as Greenwich. The difference in these 2 times could unlock your position. For every hour the local time differs from Greenwich Mean Time, you're 15 degrees away in longitude. At sea, discerning local noon, the moment when the sun is at its highest peak in the sky, is relatively straightforward. The real challenge lies in knowing the exact time at Greenwich while out on the open ocean. If navigators could solve this, they could calculate their longitudinal position with surprising accuracy. The time approach showed promise, as it didn't require lengthy observations and measurements, nor did it require complicated calculations. The only problem was, the timepieces of the day were not up to the challenges of the seafaring life. Sir Isaac Newton had this to say about the longitude issue.
One method is by a watch to keep time exactly. But by reason of the motion of the ship, the variation of hot and cold, wet and dry, and the difference of gravity in different latitudes, such a watch hath not yet been made.
On the surface, the idea of using precise time to solve the longitude problem appeared more attainable. especially to those not schooled in astronomy and mathematics. This perceived simplicity, however, opened the floodgates for a myriad of eccentric and impractical submissions to the Board of Longitude, the panel tasked with judging the solutions. Amidst these were some truly creative, albeit unrealistic, propositions. One such idea envisioned a network of ships strategically positioned across the oceans, tasked with signaling the exact time. These ships would chime bells or fire cannons at predetermined intervals, creating an auditory beacon for navigators. While imaginative, the logistics of such an endeavour, maintaining a fleet of ships in fixed locations, battling the elements, and ensuring synchronized timekeeping, rendered the proposal completely impractical. Among the more outlandish submissions was the Powder of Sympathy proposal. Rooted more in the realm of alchemy and folklore than science, this solution hinged on a fantastical powder claimed to have healing properties that worked from a distance. The idea was that when the powder was applied to an article of the ailing person, not the person directly, it would heal the person's ailment while causing a temporary sting. The side effect of the sting is crucial in the context of solving the longitude problem. The method proposed taking a wounded dog on board a ship, leaving its bandage back in Greenwich. At precisely noon, Greenwich time, the bandage would be dipped in the powder of sympathy, supposedly causing the dog to yelp in pain. This reaction was meant to indicate the time in Greenwich, allowing navigators to calculate the time difference and thus their longitude. While the idea captured imaginations, it was fundamentally flawed. The notion that a dog's reaction could serve as a reliable time signal was more than a stretch. Moreover, it raised a moral conundrum. What if the powder actually healed the dog? Would the animal need to be harmed again to continue its purpose? Amidst a sea of fanciful and ridiculous proposals, John Harrison of Yorkshire approached the problem with simplicity and genius. His conviction was straightforward. The key to mastering longitude lay in crafting a superior clock, one precise enough to keep accurate time under the harsh conditions of sea travel. Harrison, a self-taught and skilled clockmaker, was no stranger to innovation. His earlier masterpiece, a tower clock built for Brocklesby Park, is a testament to his exceptional talent. This clock has been ticking without interruption for over 300 years, a living legacy of Harrison's ingenuity. John Harrison's dedication to solving the longitude problem was a marathon of persistence and precision. Over 4 decades, he meticulously crafted 4 distinct models of his seaworthy chronometer. Each model, an evolution in accuracy and reliability, was presented to the Board of Longitude. Yet, Harrison faced an uphill battle for recognition. The board, primarily composed of astronomers and mathematicians, held a firm belief that the solution to longitude would emerge from the stars, not the gears of a clock. Adding to these challenges was Harrison's own relentless pursuit of perfection. He was a man who would not settle for good enough. Each iteration of his chronometer was a step closer to his ideal, but this unyielding commitment to precision often meant that even when one model was presented, he was already deep into improving the next. In 1759, nearly 3 decades after embarking on his monumental quest, John Harrison unveiled his masterpiece, the H4, his 4th and final chronometer prototype. H4 performed with astounding accuracy, far exceeding the capabilities of any timepiece of its era. However, Harrison's journey to recognition was far from over. The Board of Longitude, entrenched in skepticism and bureaucratic processes, subjected Harrison's creation to a series of rigorous tests and lengthy sea trials. While the H4 proved its worth time and again, the board remained unconvinced, unwilling to fully embrace a mechanical solution to the longitude problem. Harrison's struggle for recognition and the prize money continued for years, mired in petitions and appeals. It wasn't until the intervention of King George III, impressed by Harrison's work and convinced of its merit, that the tide finally turned. In 1773, after long years of perseverance, John Harrison was formally recognized for his contribution to solving the longitude dilemma. Yet even in this moment of victory, the reward he received was not the full sum promised by the Longitude Act. Following his long-awaited recognition, John Harrison entered a period of relative tranquility. He continued to tinker on his timepieces with the same passion and meticulous attention to detail that had defined his life's work. However, just 3 years later, in 1776, at the age of 83, Harrison's clock of life finally ran down. His passing marked the loss of one of history's great innovators, but his legacy was indelibly etched into the annals of time. Harrison's contributions went far beyond solving the longitude problem. He revolutionized the very essence of navigation and seafaring. His story stands as a beacon of inspiration, embodying the virtues of perseverance, precision, and an unwavering commitment to solving one of humanity's most enduring challenges. Through his life's work, John Harrison transformed our understanding and interaction with the world's oceans, paving the way for safe and accurate sea travel that has benefited generations long after his time. Thank you for watching this moment in history. If you liked this episode, please like and subscribe.